Okay, good morning, folks. This is the beginning of week 9, and I'm going to be doing two problems for you today during the first 55 minutes. So the first one is from chapter 5, and it's called Sliding Ladder. What we got here is a wall, obviously stationary, and we have a stick or a pole or a ladder that looks like that, and it is sliding. The top of it is sliding down. Obviously the bottom is going to slide to the left. If we know how fast this top point is being moved down, if we knew the speed of that top point, for example, the top point I mean the center of that circle, let's hypothetically say 5 inches per second, sliding down at 5 inches per second. And if I ask you what is the speed of the bottom point as it moves to the left, very frequently people say, okay, if this comes at 5 inches per second, this also moves to the left at 5 inches per second. And that is not correct. Even if this is coming at a constant speed, the speed of that point at the bottom is not constant. It's going to change with time. And I want to remind you where you saw something like this for the first time. Probably in your first year calculus class. So under the subject of related rates. For example, if this is y and this is z, we know that y squared plus z squared is equal to the length of the ladder squared. Pythagorean's theorem. So y squared plus z squared equal to L squared. And if you differentiate both sides, if you differentiate y squared, you're going to get 2y, y dot, plus 2z, z dot, equal to derivative of L squared with respect to time is 0. So your calculus teacher showed you that z dot plus y dot is equal to 0. And if you know z dot, you can find y dot. And it's not going to be a constant. It depends on the location of the ladder. That is where you saw this thing for the first time. Now, I'm gonna do this problem, except that I've already created the ladder and the wall, so I'm not going to bother making it. However, I want to point to something. If you look, let me zoom out of this. Okay, if you look at the center of this top of the ladder, circle on the top of the ladder, it always stays away from the vertical wall at the distance of 0.5, which is the radius of that circle. So this point stays on a line as the ladder is sliding down. This point stays on a line which is 0.5 inch away from that edge. Now, of course, you can argue that this bottom point, which I'm interested in its velocity, is also staying away 0.5 inch from the horizontal line. That is true because it's a circle, okay? Your statement is correct. However, I'm not going to use that fact that the point at the bottom stays on a line, horizontal line, just like that, except that this is vertical. I will use this line. I will not use the fact that this center stays on a horizontal line. You can use that fact and do the problem differently. But the approach that I'm going to take is only that point stays on that line. Now, if a point stays on that line all the time, it creates a point curve. I mean, it is a point curve joint. That's what Katia calls a point on a curve. Point on a curve. Point curve joint. Okay? So I'm going to create that point curve joint, and the bottom, this edge, slides on that edge. Okay? A curve slides on another curve. That is called a slide curve joint. Okay? So that's the approach I'm going to take. Point curve joint, slide curve joint, and do the problem. Okay? I could have done point curve joint, would have solved the same problem. Now, neither one of these joints can be created with a magic wand. So this is the first time probably in a more systematic way that I'm going to create 2 manual joints for you. Okay, so let's go ahead. There we are. We start with the product file. Immediately save it. File, save management. I organize my desktop so that I don't have to wander around too much. So let's see now, desktop. Yeah, see, Tuesday, lab 54. And in it, I just created the product. I will replace that. Good. Okay, now I'm going to insert the 2 parts that are already created. So insert existing component in there, and it says, okay, where is it? Desktop. Yep, desktop, right there. These are the 2 parts that are created, ladder and the wall. So let me put the ladder first. There we are. Insert existing component. Again in there. The wall. Okay, very good. So save. Now, before I move on, are there any questions? Okay, no questions. All right, so let's go to the assembly design. Assembly design, because I want to put these in the right spot. Now, one thing you realize is that I need a line. I need a line that belongs to that wall. Okay, see that this line here on the right side. I'm going to make it part of the wall, although it can be created as a new part by itself, but I'm not going to do that. Just part of the wall. And so I'm going to go to that wall. There we are. I'm in the part design. On that face, I will sketch a line. I'll clean it up in a second. First of all, I want this point. Control that line. I want them to be coincident to pull it down. Good. And I want the length of this whole thing to be 5 inches. That's because the ladder, center to center, top circle, bottom circle, is 7. So I'm going to make this thing 5. 5. The 5? Yeah. Notice that if you make this thing too long, the ladder can never be reaching the ground. Okay, basically, if it's too long, there's no way you can put the part of the ladder here, the other part on the ground, because the whole ladder is 7 inches long. Okay, good. Now this distance from that line to this line is 0.5, the radius of the circle. From here to here, the radius of the circle, 0.5. Say okay. There we are. We're going to exit, and we have our line there. Okay. Now comes the issue of putting this stuff on the right spot. So first of all, I'm going to save everything because this line that I created was not part of the wall, so it was not saved. Okay, now it is, and that's why I saved it. Okay, anchor something, the most reasonable component, which is the wall. Anchor the wall. Okay. Now I want to put this ladder, that point on the ladder. I already created a point on that center of the circle. In the wall, in the ladder, I created a point which is the center of that circle. I already did that. Okay, I want to put this at that location. So it's going to start here and slice down. So coincidence between this point and that point. Update. There we are. Okay, now I want to bring this ladder and put it on that flat horizontal surface. Now, first of all, let me remind you what the plan is. We want to create a point curve joint. That point always stays on that curve. Now, this is something, as I said, that has to be done manually, and the point must be on that curve. If the point is not on that curve, and you try to do a point curve joint later on, it'll refuse to do that. It says there is a gap between them. Make sure that the point is on the curve. The second piece of the strategy is I'm going to make a slide curve joint here. So this curve slides on that edge, on that curve. Again, in order to do that, these two curves must be touching, and they don't. Just look. The way it is, they don't. You may be tempted to use the coincidence, trying to put these things together. Let me show you what happens. So here's the coincidence that you're used to. So you're going to say, okay, I suppose you want to say that surface and this surface. The problem is that when you put the cursor on that end of the ladder, it's not going to hit the surface. It's going to take the axis of this. And if you say okay and update, this is what happens. That's no good. I cannot use the coincident, you know, with, I mean, maybe you can use it, but a lot of work. Okay, let me delete this. Or actually, and undo it, by the way. Let me undo it. Okay, good. I'm going to delete that. Is there a question? Okay. Now, what I'm going to do is, was there a question from me? Okay. This is where I'm going to use contact. So look at what contact does. Contact between this face and that face. Coincident did not do the job. And notice that there are two options here, okay? You either have external or internal. Let's look at the external that was there to begin with. You say, okay, and update. That's what I want. If this was internal, this is how it would look like. And that is not what I want. This is not, by the way, coincidence. Coincidence took that axis and put it on that face. So you have to be aware of the fact that there are features in contact that you don't have access to it in coincidence. This is why somebody emailed me a few days ago and said, well, why are you always using coincidence instead of contact? And my comment was that for those problems that we had done, contact would have done the job to create a prismatic joint and the revolute joint, etc. But there are things that you cannot do with coincidence that we're going to see later on. Right here is an example. All right, so let's save all of these. Okay, let's go ahead and create our joints. So we go to the digital markup, DMU kinematics, get the magic wand out to show you that it's not going to do me any good. Magic wand out, new mechanism, yes, mechanism 1, very good. Auto create, say okay, and there we are. It created the mechanism, mechanism 1. Degree of freedom is 1. Okay, fine, fine. The joint is revolute. I didn't expect this. And it created a joint for me. And that is nonsense. For example, if you double click on this, you make this thing angle driven and try to see what is it that it did for me. You go to simulation with command and watch what happens. This is the joint that it created. It's totally useless. So what I need to do is to go and delete that joint. Delete. I'm not going to delete the children, because if you deleted these constraints are going to go, and I may need it in future for moving around things like that. Okay. First of all, notice that the mechanism is still there, so but there are no joints. I deleted the joint. Let's do a point curve joint. So open this up, all the joints, revolute, prismatic, cylindrical, blah, 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 blah. You go down here, you see point curve joint. Click on it. Okay, it says that pick your curve. There's my curve. Remember that line that I drew? And pick your point. There's the point. Now remember, these have to be from different parts, and they are. The curve is on the wall, and the point is in the ladder. Otherwise, you can't do a joint. You can't do a joint between two things from the same part. Okay. Now, by the way, notice that there's a command here. We come back to that in a second. We say OK. Now, a slide curve. Look at all the joints that you've got. Here's point curve. The one next to it is slide curve joint. You click on it. It says curve 1. Well, I can select this or I can select that circle. The order is not important. Curve 2 is right here. Notice that as soon as I did that, it took the entire periphery of this ladder, which is why, and there is no command here. There is no command. You say, okay, notice that this was 4. After I did the point curve joint, this became 4. Now, when I do this slide curve, this is going to become 1. There is no command here. There's nothing I can do with this. But in the point curve joint, I have it's length driven. A point moves along a curve. I'm going to make it length driven, going from 0 to 5. Okay. This direction cannot be reversed. So just leave it. If you try to reverse this, it says, I'm not going to do that for you. Okay. So we say, okay, mechanism can be simulated. Let me first rewind this thing. Cancel that. Cancel. Let me update. Yeah. Okay. Good. Now. Okay. Move this. It'll move. Okay. There's no way you could have created this thing with a magic wand. Now, let's do some physics. We can create a cartoon. But that's easy. Drag this thing down. Insert. Rewind. Move back. And make it play going up and down continuously. Oh, what did I do here? Let's do it again. I think I said cancel. Okay. Yeah. Okay, so anything but 1 and play. Up, down and up and down and up. Of course, going in one direction is going to make a big jump. See that? See that? Going in one direction. Fine. Everything is working. Okay. Let me say okay. Good. Now, when you make that simulation, it will give you the opportunity to compile it, make a video clip. It will give you the opportunity to compile it and make a pre-play. Get the trace, for example, right? You need to compile it to get the trace of a point, whatever that point is. I don't know. Now, I want to put some physics into this, and the physics is I'm going to give the speed of this point. So you click on f of x, okay? And for the mechanism, you click on the mechanism, so you get only 2 things, the time and the command. The command is length, of course. Add a formula. You select it, add a formula, equal to 1 inch divided by 1 second times time. Double click on it. No bad messages, so everything was units matched, everything. Now I want to plot the velocity of this point. Okay, so first thing I need to do is to create a sensor. The reference product is this. Okay, and the point is that point. That reference product, all it means with respect to what part you want to create that plot. Okay, in this case, we want to create the speed of that point with respect to stationary coordinate system, which is the wall. You say okay. Now we're going to go and do simulation with laws. Remember, this thing was 5 seconds. Remember, sorry, this thing was 5 inches, and I gave the speed of this as 1 inch per second. So it's useless to go after 10 seconds, because after 5 seconds, this reaches down here. Actually, after 4.5 seconds, because you have to count the radius of that circle too. So 4.5, at 4.5, that should become horizontal. 4.5 seconds. Activate your sensor. Activate your sensor, and that sensor is the speed. Notice that there is x component of the speed, y component of the speed, z component of the speed. When you say linear speed without any x, y, z, it means that the magnitude of these things, which is square root of this square plus that square plus that square. You know, the stuff that you're doing. Move this thing out of the way. Play it. There, after 4.5 seconds, it became horizontal. And graph it. And there we are. So the velocity of this point is not linear. And if you say, what is this? That's okay, because there is no way you can give it an instantaneous velocity of 1 inch per second right away. So there is a kind of discontinuity at the time t equal to 0. How can a ladder suddenly start sliding at a constant speed of 1 inch per second? You can't do it, okay? So that's why you have to ignore this anomaly here. This is the way the speed is going to look like. Now, I want to show you something, because some of the people who did the homework for this last homework, or they may be doing the next one, you see this graph? You see this so nice and smooth? You see this so nice and smooth? Okay, let me close this, rewind that, clear my history, and all I do is to say the number of steps. Let me go and do 5, and then play it. It's going to be very fast, of course, and look at the graph. There we are. This is the same graph, except that because you said, give me only 5 frames, it interpolates linearly between them. Remember, it was nice, very sharp rise, and a nice drop. Okay? And let me try it for you again. Rewind, clear the history. This time do 80. It's going to, of course, that means that this is going to go slower, slower, slower. It's not affecting the speed, but as far as capturing information, it affects that. That's why when you do it only 5 times, you get that broken line. You see that? Even this is kind of made smaller. So people on the homework, a few people, you know, contacted me yesterday in the lab. They said, how come our graph looks different from yours? And then I said, did you use a different number of steps than mine when we were playing with it, probably? And the answer was, yeah, when they changed it back to what it was supposed to be, you know, they got the same thing that I got. Not that I always get the right answers. Now, remember, these things, you have to capture the screen, paste it in the Word document, save the document as we instruct you, because on the test, we're going to ask you to do certain graphs. And the graphs must be exactly what we are asking for. You cannot give me 5 graphs here. Only the thing that we want and only the right things. No part marks. And the units we specified. So any mistake that you make in giving us the wrong graph, giving us multiple graphs, giving us the wrong unit, you lose the marks for it. It's not substantial, you know. 100, I don't know, out of 100 points, you may lose, I don't know, for that particular problem, 2 points. Okay, that's good. That's good. Now, I could have done this. Say this is done, but I could have done this thing instead of a slide curve, another point curve here. You would have drawn a line here. You would have created a point curve joint, and then again you make this thing length driven, or you make this thing length driven. Whichever you know. Okay, and solve the problem. Are there any questions? Can you please say it? Okay. I'm going to kill this. If that question is for me, you have to speak up. Now, the second problem that I would like to do is this problem. So we have a gearing mechanism, and we have a little pinion here, which is attached to a motor, perhaps. And this thing turns. It makes that thing turn. And that thing is attached to a rack. This is called rack joint, okay? As the big gear turns, the bottom rack moves to the right or to the left, okay? So this is the mechanism that I'm going to do it, and I'll do it two different ways. The first one is just like it's done in chapter 6. I'll do that. And then towards the end, I come back and say, okay, let me do this thing problem for you differently. Okay. Now, yesterday in the lab 53, when I did that portion, the last, I don't know, 5, 10 minutes, no, it wasn't 10. The last 5 minutes, I ran into some issues with getting the problem to work. Okay, no problem. It happens. So if you watch the video for that lab, you'll notice that things got out of hand in the last 5 minutes. So I basically had to swallow my pride. I said that I can't do it. You guys can. You're better than I am. Okay, but once time subsided, I looked at the issue, the mistake that I made, and fixed it. So we're not going to have that problem today. Okay, I hope. All right, so for your reference, I have made the parts. I'm not going to make them. And those people who may want to repeat these things, these are the dimensions that I put in there. These are not the same dimensions in the book. And I have, this is called driving gear or pinion. This is the driven gear. This is the big one. And there's a rack and there's a base. Okay, the only thing that I know is that the radius of this rack, the radius of this pinion gear is 1 inch, for example, and this is 2 inch. And let me remind you some of the stuff that you did last summer or probably last summer machine design course. Honestly, I'm not sure whether you do that last summer. You did that last summer or last winter, this past winter, in failure for design prevention or something like that. No, wait a minute. Not failure for design prevention. Design for failure prevention. That's what it is. So I don't know whether you did gears there or last year, but anyway, when the radius of this is 1 and the radius of this is 2, it means that the speed of this is double the speed of that. So when if this thing goes at, I don't know, 50 RPM, this guy is going to go down at the 25 RPM. And the other thing is that the number of teeth on this, obviously, is half the number of teeth of that. But just remember that. You don't have to remember it for me, but when you look at the result, perhaps we can refer to that. Okay, so first method. We start with a product. And I don't know where I put those files. We'll see. So we go product. And immediately we're going to save this thing, file, save management, save as. This is lab 54, except that I'm going to call this thing a new folder. I'll call it gearing mechanism. Okay. Now I need my parts, so I'm going to get my parts. So let's see now. File, save. No. Insert. Existing components in there. Now let's up gearing mechanism. This is the one that I just made. Yep, that's not here. That's the one that I just made. Mechanism. Somewhere must be somewhere here. Oh, my gearing system for using. Okay. So there is a base here. Okay, let's put this thing there. Open. Excellent. Insert existing mechanism. We have two gears, so the driven gear and driver gear. So this one, shift that one. I'm going to put it there. Okay, and insert existing component in there. And I want the rack. That was the rack, yeah. Okay, good, good. So save everything, go to assembly design. Save everything. And let's move these things apart so that we can see what's going on here. Before I do that, actually, you know what? I'm going to anchor the base. Okay, I'm going to move these things apart. For example, translate this one in the X direction, and this one in the X direction, and this one in the X direction. So we can see what's going on. Now, the shafts are actually, these are the shafts. These are the shafts. These indentations, I made them because I want you to see that the gears actually turn. Because if you just look at the circle like that without a marker or indentation, you won't notice that this is turning. So the only reason I put these two guys here is so that you can see it. I should have done pockets so that it was not as disruptive as what it is now. But the shafts of the of these gears are here. Okay, good. So let's go ahead and do our problem. I already anchored this, so this is not going to move. I think I did. Yeah. So let's mount the driving gear or the pinion in that hole. So coincidence between the axis of this and the axis of that hole. And again, you can use contact or coincidence. I'm not using contact, I'm using coincidence. So this face and that face. Now you want these two to be facing each other. So my guess is that you want them to be reversed. If it doesn't work, fix it. Oh yeah, it is good. See, it worked. Okay, good, good, good. They have to be facing each other, those things. So let's do the other one. Coincidence between that hole and the axis. This is the axis of the shaft, and coincidence between this face this face and the face of the base. And again, I want these things to be opposite. Like you can either click on these green arrows, or you can change these things to opposite and say okay and update. And there we are. You see that the shafts are sticking there. These are just the indentations. I don't particularly like it. You know what? I'm going to make those things shorter so that it doesn't distract us as much. So let's go here. This is the pad. What is it? 0.7. I'll make it point. I don't know. 0.1. We'll do it. Yeah, that's better. 0.1, and the other guy driven. This one, 0.1. I was not thinking on it. I usually make pockets for those purposes, but anyway, back to there. We're going to save everything. Okay, good. Now let's put the rack in there. A coincidence between this edge. Oh, wait a minute. Oh, not contact, not contact. This edge and that edge. And of course, when I update, it'll go back and sticks to that. This is fine. There we are. Okay, good. All right. Now, notice that I did create, and by the way, notice that this rack goes along that edge to edge, and then face to face. So edge to edge. So for example, this face. Something is wrong here. Just a second. Coincidence between this face and that face. Now you know what it's going to be. This is going to become a prismatic joint. You already know that because I did this edge of the rack and the edge of the base and the face of the rack and the face of the base. That's going to become prismatic later on. So we save everything. Now we're going to go to digital markup. the MU kinematic, get the magic wand out, new mechanism, auto create, say okay. And I hope by now you have an idea of what kind of joints we're going to have. We're going to have a revolute here, a revolute there, and a prismatic there. Okay, so let's check it out. Revolute, revolute, prismatic. And this is why the degree of freedom is 3, because a revolute joint has 1 degree of freedom. There's 2 of them, that takes care of 2. And the prismatic joint also has 1 degree of freedom, so the total is 3. Okay, good. Now, first method is I want to show you some of these joints that you have not used before. In the first example, we use point curve and slide curve. If you scroll down to the right, you see, there is a gear joint right there. Gear joint. In the second attempt, I'm going to come back and do it without this gear joint, a different way. So let me click on the gear joint and look what it's asking you. It says, oh, you need to give me 2 revolute joints. Right there, revolute 1, revolute 1. And I already created those. This is why I don't have to worry about this create button. I already created those. So let's go pick it. Here is revolute 1, and here is revolute 2. And then it says ratio. What is the ratio? The ratio is 0.5, okay? Because this was 1, this was 2, depending on which one you pick first. If you don't know, just click on the define and select this radius and that radius, and it's going to give you ratio 0.5, okay? Now, are they going in the same direction or opposite? Well, they are going in opposite direction because these are externally engaged gears. Right there. Not the same, opposite. And then you say, okay. Notice that the degree of freedom became 2. Okay? Now, this guy and that big gear, they make what is called a rack joint. So immediately next to it, immediately next to the gear joint, you see a rack joint. You click on it, look at what it's asking. Give me a prismatic joint. Well, I already have one, I created one. But the revolute joint got eaten up by the gear joint that I just created. You see that? Those 2 revolute joints, gone. I don't have access to them. This is why you have the opportunity to create it now, again. And that's what I have to do. I have no choice. So create. It's asking you for axis and axis. Remember, we're dealing with the big gear, axis and axis. So axis of the big gear, hide the big gear, axis of the hole, face of the big gear. So let's put it in hiding. Let's go get it back. Face of the big gear. Let me hide this guy. There's the face of the big gear and the face of the base. And there is the face of the base. This is the revolute joint. I already created this, but I got eaten up by this gear joint that I created. And this is pretty much it. By the way, when you create revolute joint, I want to bring something to your attention. If the faces match, if the faces are mating each other, they're sitting on top of each other, this is null offset. But a revolute joint can have offset too. In other words, 2 faces can be separated by some amount, and then of course you select this offset and it gets it for you automatically. You don't have to worry about that. You see that? It did it. Say okay. By the way, this ratio, this it says define. Give me a value, but let's confirm that. So define. All I have to do is to select this radius, and it gives you ratio of 3.19. And what that means is that for every turn of this, for every turn of that, this thing advances by 319 millimeters per turn. You can change these so that it's inches per turn, etc. But that's okay. I don't need it. Look at the degree of freedom equal to 1. So I have many choices here. I can make in the gear joint, I can go to the gear joint, make this thing angle driven, or I can make this thing angle driven, or I can go to my rack joint and make this thing length driven, etc. But that's what I'm going to do. I'm going to go to the gear joint, double click, and I'm going to make angle driven for Revolut 1. Revolut 1 was the one for the pinion. And I go between 0 and 360. Actually, let me make it 0 and 720. How about that? So that this thing goes once, this thing goes twice, this thing will go one, advances once. So, I don't know, I'll make this thing 720. 720. That's 74. 720. Okay, mechanism can be simulated. I'm not going to put any physics into this. The physics, you can do that. You have to give it angular speed and things like that. But anyway, so if you do a simulation with command, well, let's make a mechanism actually out of this. A cartoon, basically. So insert, rewind, anything but one, and make it go forward and backward. If you want to go in the same direction, just make the arrows chasing each other. Okay. So this was using the gear joint and the rack joint. I want to do this problem a different way for you. Okay. So are there any questions here? Okay, no questions. So I'm going to delete my mechanism. I'm going to delete this. Actually, you know what? Let me delete the joints. Delete this joint. Delete the rack joint. Delete all these what's going on here? This shift control, no, this shift, no. Okay, delete. Don't delete the children. Okay, good. No joints. No joints. All right. So the two Revolut joints, let me make a Revolut joint here for this one. So we go through it. Revolut, I'm do that manually. Okay. So for the pinion, it's this axis. Hide that axis, and the plane let me hide this, that plane, and this plane. We say okay, good. We have a Revolut joint between the driver and the base. Okay, now I'm going to do a roll curve joint. Where is it? See that? Look at your joints. Here was point curve, the slide curve, roll curve, right there, roll curve. This curve, and that curve. So as this thing moves, this rolls on it. It's not sliding. And we say, okay. And I want this big circle to roll on that edge. So another roll curve between this circle and that line. Just remember, don't complain on the test. If you have a problem with point curve, slide curve, roll curve, points must be on the curve. For slide curve and roll curves, curves must be touching. Okay? So, good. All right. Now, okay, so let's make a prismatic joint between this rack and that base. So let's do that. So prismatic between this, let me hide that, and that, and planes. Let me bring this in the front so that I can see what I'm doing. That face and that face. We say okay. Degree of freedom is 1. Okay, good. So that first revolute, this revolute, we're going to make it angle driven. 0, 360. Mechanism can be simulated, and let's do that manually. Move this thing out of the way. There we are. This is the driven gear, or driving gear, which we turn it. It makes the other gear roll on it. It makes the rack roll on that, or advances because of that big gear. Now notice that I did not use the rack joint or the rack joint or the other one, the gear joint. I did not use it. Now let me do something else. Let me delete this. Let me delete this. And do a different kind of a joint down here. Excuse me. Okay, so planar joint between this plane and that plane, and another planar joint between the back of this and the front of that. And we say, okay, hallelujah. It's the same thing. When you think about it, doing two planar joints, the way I did it is equivalent to saying that, oh, those two edges move on each other. In other words, these two planar joints had the same effect as the prismatic joint. The moral of the story is this. The moral of the story is this. Two people may be doing the same problem using different joints. As long as it produces the same effect, they're both acceptable. When you do your problems, you may be doing something which is different from what I do, and you say, oh, mine works too. Sure, there's no reason it didn't. Like here, we did this problem with three different types of joints. The first one was using the gear joint and rack joint that's available directly in CATIA. Okay, but you don't have to use that. This is fine too. Both acceptable, all acceptable. Are there any questions? Okay, there are no questions. It's 50 minutes, that's good. So I'm going to stop the recording of this, and this is what I'm going to post on YouTube.